Hi, my name is Dashya Chaudhary, and today's video shows a comparison between the observed constant velocity motion of one of my lipstick tubes in comparison to its predicted motion, which I calculated using both the tracker and VPython software. The purpose of this lab was to analyze the motion of an object moving at the same speed in the same direction, in my case a lipstick tube, and applying Newton's first and second laws to explain the recorded observations. So first, I recorded my observations from rolling my lipstick tube on a flat surface. I assumed that friction and atmospheric forces were negligible. Here's my clip of the lipstick tube being rolled, and it moves in the negative x direction. As you can see, I set my time frame to begin from a certain point in the video after my tube had begun rolling at a constant velocity in order to avoid errors that may occur from the initial force my hand applied to provide momentum for the tube's motion. In the case that I flip the orientation of the axes on tracker, my linear graph, as you can see in the right corner, would be reversed and rise in a constant velocity to the right in the direction that my mouse is moving, instead of what I have shown here. Well, if you notice that my first frame on tracker was set in the origin of the system at the center of the tube at time 0. The negative side of the x-axis here is shown to indicate that the ball moves in the left direction. The point masses for this tube were also tracked for multiple frames in the center of the tube, and measurements were calibrated to the diameter of the tube, which was 0.018 meters. For my system, the tube, I assumed that all external forces like friction and air resistance were negligible. So now I'll show you my VPython coding, which I used to predict a model for the tube's motion. And as you can see, my net force vector is 0. Because if that were not the case, using Newton's second law, either the mass or change in the time delta t would have to be 0 for the velocity of the tube to remain constant. And neither of those two values could be 0 for this system. Also, for the model motion, I lowered the time interval ranges to 0.002 seconds because my entire video is only 0.76 seconds long, and at the preset time the model seemed to remain unmoving. I also changed the parameters of my origin and trail curve to fit my model's updated data, which you can see right here. Here's the test run for my model predicting the tube's velocity. As you can see, the time frame is very short, and it only shows a little motion. Now, comparing the graphs for both experimental and modeled observations, notice that they both start with the same initial velocity and initial position data, and so both these points lay directly on top of each other. However, both graphs deviate after this point. The red line shows the predicted velocity of the tube and is completely linear because I had set Fnet equals 0 for the calculations that were done on VPython. However, the blue line representing experimental observations deviates from linearity. These deviations in velocity, due to forces such as air resistance, friction from the table surface, as well as friction from the slight bumps or letters that were basically printed on the tubes of the lipstick. These forces may have caused the blue graph to deviate from the model version, with 0 net forces acting on the tube. The deviations, which you can see, are that it's raised from the red graph right here. So, to conclude, this was an interesting lab, and it made me understand that Newton's second law of motion is actually Newton's first law of motion when the net forces are all 0. Hope you guys enjoyed this lab, and I look forward to presenting more about this next week. Thank you.